Hello everybody. I apologize for taking so long to get to this. We've had an inordinate amount of problems with Canvas, and we finally got this straightened out. I hope everybody's enjoying their time out, and so let's get started. I want you to remember that when we looked at the scalar ODE, du by dt equals lambda u, where lambda is a real number, and the user specifies the initial condition, then there's really, the solution is very easy, separation of variables. And then the only thing that can happen in this simple case is that if the lambda is equal to 0, then this is a constant and your solution is just the initial condition. Not very interesting. If lambda is less than 0, this decays and the solution goes to 0. So for example, if this were population dynamics, that would mean that the population goes to extinction. If lambda is bigger than 0, then this goes to infinity and the squirrels overtake the universe, which is nonsense. So that can't possibly be a very good model. So what we do is we extend this now to a system of equations. So in other words, I have two unknown variables, u1 and u2. And here for now we're just going to assume that this is a constant matrix, coefficients. And the user has specified what u1 is and u2. Typical example of this are two competing species, okay? Or two species symbiotic, whatever. And so it looks like, so if I rewrite this as the matrix A, constant matrix, then I have du by dt as a vector. So this is a matrix equation, and it looks very similar to our scalar ODE right here. So we suspect that maybe there's a way to take this solution to our scalar problem and see if we can somehow adapt it to our matrix problem or system. So if, for example, the matrix A is a 3 by 3 matrix, then we obviously have a bigger, higher dimensional problem, etc. So if we go back to the solution of the scalar equation, we know it looks like this. So it's going to be an initial condition times the exponential part. Okay, so we suspect, whatever, that maybe we could somehow use this to get the solution to this guy. And that's where we're headed for today. So instead of having the initial condition being a scalar, we're going to have it as a vector, and instead of e to the lambda t, we suspect that it might be e to the at. And we started talking about this in class before things had gone crazy here. Now if I take a look at the dimension of the initial condition, it's you have n rows and one column. So if n is equal to 3, we have 3 species populations. Then this is going to be a 3 by 3 matrix as well. And so, or excuse me, this whole thing should be an n by n matrix. Now let's see what happens if I take my matrix equation and I take a look at the dimensions. This is very important. Dimensional analysis could get you a lot of mileage. So this is an n by n, this is an n by 1. These two guys match up. So that means the final result on the right hand side should be an n by 1. And notice that the derivative of this vector is also n by 1. So it makes sense. You don't have a conflict in the dimensions. So the dimension on the left side should match up with the dimension on the right side. This is a very common mistake that students make when they're coming up with mathematical models, is they don't get the dimensions correct. So if we try to do, so we took the scalar equation and we have a solution. Now, suppose we try to write the solution to this problem as the initial condition times this matrix exponential, which we have not defined how to do that. When you have an equal sign, the two dimensions on both sides better match up. Otherwise, you've got a big problem. Well, if I look at the left-hand side, that has what? N rows and 1 column. Now, what about the right-hand side? Well, this is an n by 1. That's your initial condition. This is an n by n. It doesn't match up. This can't be correct. This doesn't even exist. You're not allowed to multiply those two things. So how about we reverse these? Remember, in matrix algebra, multiplication does not commute. So in this situation, I'm not even allowed to multiply these guys. Let's reverse that. Let's put the e to the at first and the unit. Does that work? Well, let's see. This is an n by n. This is an n. I've got to pull this up a little bit. Sorry. Let's pull that up a little bit. This is an n by n. This is an n by 1. These guys match up. Makes sense. The result is an n by 1, and left side equals the dimensions are equal. Makes sense. Okay. So it appears that this should be our solution. And some of the things that should happen is if t is equal to 0, then we're going to get e to the 0 matrix, which we hope is a what? N by n matrix with all zeros in it. It's all ones in it, excuse me, because you're exponential, so it should reduce down. We're going to have to be a little bit more precise than that. But the big question is, what in the heck does e to the at mean? All right, so I want you to remember from Calc 2 that when you have, and now what I'm doing is instead of using x's, I'm using boxes for an arbitrary object, and this is actually going to be an operator. So if we have any hope of figuring out what this means, one attack is to write it as in its Taylor series. So if I take a simple example, all right, so if I take the x by dt is 1x plus 1y, y by dt is, did I do that right? No, 1, yeah, 1, yeah, this times this, and then this times this, right? So if I try to use this form, I'm going to get myself into big trouble very quickly. And here's why. Let me just pause this for a second. Okay, sorry about that interruption. So if I take an example, a simple 2 by 2 matrix, and I try to use this series expansion, we are going to get into trouble really, really quickly. So instead of 1, obviously we mean with matrices the identity with 2 by 2. So what I'm going to have to take, so in place of box, I'm going to put, I'm going to put this, then I'm going to put this squared over 2 factorial, etc., etc., etc. And this is going to get messy very, very quickly because you're taking a matrix and you're raising it to the power 2 and then 3 and 4, etc. And so if I use Mathematica, so I create the matrix A, and I just check to see because you guys know I'm a horrible typist. And now when you go to do matrix multiplication, you have to use the dot here. Do not use the asterisk. That means something. It means just take 1 times the 1, 1 times the 1, 4 times the 4, negative 2 times the negative 2. That's not what you're looking for. This is not a course in scientific programming, so I don't want to get into all the subtleties of how to get around stuff like that. But if you notice that your matrix here in powers, so we start off with A, pull this up a little, so then we square this matrix, and then we cube this matrix, and you notice that the entries are getting what? Very, 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 very large. So that is not going to be the way to go. I want to remind you of when we talked about the geometric meaning of the eigenvalue problem, remember what we did was we took the unit circle, and the reason we're doing this in the Cartesian is because we just have two variables, x's and y's. And remember what we did was we took these points right here on the unit circle, we took our matrix and we transformed them. In other words, what was originally 1, 0 now becomes 1, 4. So we would go 1 and then up to 4. So what we're thinking about is the matrix is actually acting on points and transforming them. And we could do that. I'm going to go through this very quickly because we've already done this in class. So then you could take the point 0 and then 1, so it's on the north pole, and we transform that. We get a new point, which I'll call B prime. Please, it's not a derivative. It just means it's another point. And so what we could do is we could plot. So here is originally where 1, 0, and it gets sent over to here, and then B gets sent down to here, and where C gets sent to here, D gets sent. It's not obvious what this transformation is doing. So what we do is, instead of just transforming those particular points, let's take the unit circle. So if I go to polar coordinates, any point can be described as the what? In terms of r and the angle theta. And so if I would let the r be equal to 1, then that is x is going to be cosine and y is going to be sine. So anybody on the unit circle can be described as this point. Let me turn off my messaging stuff. And so what I could do is take the transformation. So we know what cosine sine is. It's just taking all the points on here. And so Mathematica has a command called parametric plot. And what that is, so what I'm going to do is just to check, I'm going to call this graph 1. There's a reason I have to use this plot range. I'll talk about that in just a second. So I'm going to create the first graph, which is just going to transform. So it's going to take the unit circle. I'm going to let thetas go from 0 to 2 pi. And clearly we get our what? Our unit circle. Okay, so now if I call my second graph, so now I take my matrix and I take the dot product of the unit circle and I get an ellipse. Okay? And when I called it G1 and G2. Now remember in the G1 I said plot range 5. What I'm saying is because this guy is roughly between negative 4 point something, 4.5 and positive 4, just so they can get both pictures together. And you see what this has done is this matrix A has transformed the unit circle into an ellipse. And if we look at so if we take the eigen system, so this is built-in Mathematica command, and it's easier to look at it if you put it in table form. So what this is saying is Mathematica has calculated I have two eigenvalues, a -3 and a 2, and this is the eigenvalue -1, 4 associated with this eigenvalue, and 1, 1 is associated with this guy. Now think about this, a -1, 4. Boy, did I screw that up. Oh, it could actually be the other way around. It doesn't matter. This could be actually 1 and -4. I don't know why that should have been up here, like this. Sorry, it doesn't matter. And what does 1, 1 look like? Well, it's a vector that looks like that. And if you go back to your picture, let me see if I did this with the... If you go back to the picture here for a moment, it looks like you do have like a -1 and a 4, but it's over here. It's not 1, 4. I'm sorry. So you have your major and minor axes, and so without bogging down in all the details, all you're doing is the idea behind the eigenvalues and the eigenvectors is the stretching or compression along the major minor axis. So let's go back to this problem here. So if I do this by hand, I'm looking for a vector so that when I take this matrix and I transform this vector, I transfer it into the same vector except what? Compressed or stretched, or possibly zero, which is not interesting. So if you go through the algebra here, you just write this as a what? Because you have to write the this is a matrix times a vector so that you can put these two guys together. So if I bring this over, I throw in the identity matrix, I subtract from both sides, and I rewrite this as a matrix times a vector. Okay, and so what's happening is you have a matrix times a vector equals the zero vector. So if I think about this, this is AE equals the zero vector. So if I was to ask you to solve this as a scalar, if the right-hand side is 0, it means this has to be 0 or this has to be 0. If this is 0, then yeah, it's a trivial solution, which means somehow the A matrix somehow has to be 0. Okay, so this turns out to be your, if you look at your characteristic polynomial, it's a 2 by 2. And this is telling us if it's 0, then these guys have to be dependent, not independent. And if I just expand things out, I get my polynomial is this. Now, just to remind us about something, if I come up with a number so that when I substitute into a polynomial I get 0, it means lambda minus that number is a factor. So we just kind of screw around here. If I put in a 2, I get 4 plus 2 minus 6, which is 0, which means lambda minus 2 is a factor. So we can go through our long division. And so I take lambda minus 2 into this. So what times lambda gives me lambda squared? Well, that would be lambda multiply. So if just thinking of this as long division with a 3-digit and dividing a 2-digit into a 3-digit. So lambda times that is lambda squared minus 2 lambda, subtract. Whatever was positive becomes negative. Whatever is negative becomes positive. 2 lambda, lambda is 3 lambda, bring down the 6. What times lambda gives me a 3, obviously 3. Multiply, and guess what? You get a remainder of 0, so we can factor that. Everybody okay with that?